So in this video we're going to continue discussing joint random variables slash joint distributions, and we're going to discuss, and in this video we're specifically going to discuss marginalisation, which is we've seen how there are these kind of two ways of viewing joint random variables. Either you can view it as you have two random variables defined on a single probability space and they form a joint random variable, or you can view it as we make a mapping from our abstract probability space onto R2, set up a probability space that's homomorphic to our original one on R2, and that's another way of viewing joint random variables. And we've seen how you can go from having two random variables to getting a joint random variable to getting this sort of R2 picture. What we want to see now is if we've got the R2 picture, can we go back to having two random variables? Okay, so let's have a look at this example that we've been seeing a lot recently. So this square. So we pick a point in the square randomly, and we have so far seen its CDF and we've seen its PDF, and we know its PDF, its joint PDF is 1 everywhere, which we'd expect. We want the probability density to be uniform everywhere. Okay, so let's now say that we have a joint random variable here, which is mapping each point onto a ordered pair of real numbers. So 0, 1, cross 0, 1. So it's describing every single point an ordered pair of real numbers. So let's do some specifics. It ascribes this point, it ascribes that 0, oh dear, not like that, 0, 0, that's the ordered pair it's going to ascribe there. It's going to ascribe this point 1, 0. It's going to ascribe this point 1, 1. Oh dear, this pen's going already. And it's going to ascribe this point 0, 1. Okay? And we can think also, oh dear, we can think also of it ascribing this point in the centre a half, half. Okay, so it's given every single point in this square, it's given it an ordered pair of real numbers. So how do we go back to the two random variables we saw in the first video on joint CDFs? So we had two random variables, remember, x and y, and x ascribed to every point its x coordinate, so it ascribed you a number between 0 and 1, and y ascribed you a y coordinate 0, 1. Okay, and these were two random variables here, and it's ascribing, if you think about it, the x value is ascribing points on the same vertical line. So all these blue points, it's going to ascribe the same x number, and it's going to ascribe all of those a half, basically. So what we can ask is, okay, this is a probability distribution over here. Well, it's a probability space, so it has and it's in the real numbers, so it has a probability distribution. What's its PDF? Well, it's going to be uniformly distributed because it's equally likely to take any on any x value. So we know that x is going to be uniformly distributed on 0, 1, and therefore it has marginal PDF fx. So the marginal PDF of the random variable x as a function of little x is going to be equal to just 1. And similarly, y is also going to be uniformly distributed. So y ascribes all points on the same horizontal line, so all points with the same y coordinate, it ascribes the same y value. So y again is uniformly distributed on the interval 0, 1, and the marginal distribution of y, the marginal PDF of y, is again just equal to 1. So what we want to know is if we're given the joint PDF as a function of x and y, so this is a function ascribed to R2 rather than R1. So each of these PDFs is just a function of R1, whereas these are functions of R2, and it's ascribing to every single point on this interval 0 to 1, it's ascribing the value 1. So on this square, rather, this interval 0, 1 cross 0, 1. So on this square, it's all ascribing the value 1, and everywhere else it's ascribing 0, and similarly these are only ascribing 1 to the values between 0 and 1, and 0 everywhere else. What we would like is we'd like a way of going from this back to this. So there is a way of doing that, basically. If I want to know what is the probability density that you have a single x value, well, I can just integrate over all the other y values. So basically, what you can think of is at the moment, each of these individual points on this blue line, say, which all have a constant x value, are being ascribed a separate value in here. What I want is to kind of combine them all together just to get one overall value for x. So, I want to, the way that I would do that, the way that I get the marginal distribution of the random variable x as a function of x is to just integrate out y. So I want the integral over 0 or 1 of the PDF, the joint PDF of these, and I want to integrate that with respect to y. So the way you can think about this is that probability density is kind of like the tiny infinitesimal version of probability. So by adding up and integration is kind of the infinitesimal version of summing up. So what I'm doing by integrating from integrating over the vertical lines basically is I'm adding up all the probabilities that you're at all of these points, but of course I can't add up the probabilities because the probabilities are all 0, so instead I'm adding up the probability density function, which is the infinitesimal version, if you like, of probability. So I'm adding up all of these, and that's going to give me the probability that I'm overall at that value x, but of course we're still infinitesimal, so it's going to give you the PDF that you are at a value x. So if I do this calculation, I would integrate from 0 to 1, the joint PDF is 1 dy, and this is just going to give me, by the second fundamental theorem of calculus, its antiderivative is y, and I just need to evaluate it between 0 and 1, and I get 1. So that is called x-marginalization, and basically marginalization is how you go from the joint distribution and you get back the marginal distributions, and in this case it's x-marginalization because we're getting back the x distribution. Similarly, however, we could go in the opposite direction. We could do the other one if we want the if we want the marginal PDF of y. So in other words, if you've got, again I'll go over the intuition, if you've got this box in R2, these are all the values that your joint random variable can take on, so all these ordered pairs, and you want to know what is, in a sense, the infinitesimal probability that you are at a value y, then that is the sum of all of these possible values of x that you can take on and still have the same value of y. And the way that we sum up infinitesimals is using integration. So we integrate from 0 to 1 the joint PDF as a function of x and y, dx here, and basically what we're doing is we're summing up all these infinitesimal probabilities that you're at the point, at one of these specific points, and if you sum all of that up and the equivalent of that is integrating, what you get is the probability that you are at a specific y value. But again, it's still equal to 0. It's still actually, the probability is still equal to 0. So instead what we end up with is an infinitesimal probability, i.e. a probability density function. So again, this is called y-marginalization here because we get the marginal distribution of the y random variable, and in this case we integrate from 0 to 1. Again, the PDF is just 1, so we integrate dx. And again, by the second fundamental theorem of calculus, the antiderivative is x, evaluated between 0 and 1, and you get 1. Okay, so the marginal PDF of the y value of y is f marginal y, as a function of y, rather, little y is equal to 1. So again, it's a uniform distribution on the interval 0 to 1. So y is uniformly distributed on the interval 0 to 1. Okay, so this concept of marginalization, how you can go from having this function of this joint random variable which is ascribing to every outcome an ordered pair of real numbers, how you can go backwards to getting a distribution on just a single real number. The way you do it is just integrate out one of the components basically, and that's called marginalization.